Hi everybody, I'm not sure what happened to my software, but it abruptly closed. I was able to save the first half of what I recorded, or the first part of what I recorded, so I guess that'll just be part one of the video, and here's part two. So where we left off was that we were going to tackle this function that represents some data set, right? N drive-in movie sites in the United States is the number of drive-in movie sites is governed by this equation, such that T is the number of years since 2009 for the period 2009 to 2014. So that means that possible values for T are 0 to represent the year 2009, 1 for 2010, 2 for 2011, 3 for 2012, 4 for 2013, and 5 for 2014. Okay, so anyway, but that's neither here nor there at the moment. We just want to rewrite the equation using the function name f. So certainly we're going to use f, let's use this purple color, as the function name, but the input variable is what? Well, the variable in play for the function itself is t. So this is going to be f of t equals, and then go ahead and just copy down exactly what you see there. Negative 0.49 t plus 381. All right, great. So what does f of 0 represent in this situation? And we need to find its value. So f of 0 is negative 0.49 times 0 plus 381. So essentially, this first term zeroes out, and we're just left with 381. So hopefully everybody can see that pretty clearly algebraically. So f of 0 is 381. So that is to say that there were 381 drive-in theaters. Oh, you know what? I vaguely remember this problem as being a typo with the period right there. So let me just address that at the moment. Just cross out that typo of a period, cross it out there, and just pretend that it's not there. It should be negative 49t plus 381. We shouldn't have that decimal there. Sorry about that, guys. That is a bit jarring. But yeah, that's a typo on my colleague's part, which I should have caught and removed, but I hadn't done that yet. Okay, so just disregard it for the time being. Actually, let's erase it here too. Great. It's supposed to be negative 49t plus 381. Cool, 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 cool. Going back to where we were, 381 drive-in theaters in 2009, which remember, that's supposed to be the year representing the 0th year, okay? Now, find f of 3. F of 3 is going to be negative 49 times 3 plus 381. Okay, so having a negative slope, in fact, that's negative 49 is the slope. That's how many theaters are lost every year. How many drive-in theaters are lost. So negative 49 times 3 equals 147. We're going to subtract that from 381, and we get 234 left. And 3 is 3 years past 2009, so that'll be 2012, okay? So what does it mean in this situation? There were 234 drive-in theaters in 2012. That's what that means. Okay, cool. Again, let me just, before we move on, address the fact that there was a typo. The little period in front of the 49t after the negative sign was not supposed to be there. So make sure that you're removing that in your work here, and which you did, I'm sure, while you were following along with me. Okay, great. Moving on. We have a new scenario here. Ooh, about eating ice cream. Yum. It says that it takes a person 5 minutes to eat all 12 ounces of ice cream in a cup at a constant rate. Let f of t be the number of ounces of ice cream remaining in the cup t minutes after the person began eating the ice cream. Find a linear equation of f. Write your answer in slope-intercept form using function notation. So there's a lot of stuff that we have to just come up with here based on the information that was given in the example. Okay, so if it takes 5 minutes to eat all 12 ounces of ice cream, well, then there's some ordered pairs that we could come up with. So at t equaling 0, how many ounces of ice cream do we have? Well, we have 12 ounces of ice cream, so that means f of t equals 12. 0 minutes have elapsed, so all 12 ounces are present. Okay, now let's entertain another scenario in which the 5 minutes have elapsed. Well, then how much ice cream should we have left? Well, it was stated, oh, sorry, let me put the outputs or the inputs inside of the function. That's supposed to be correct notation there. My bad. So f of 0, therefore, is 12. F of 5, after 5 minutes have elapsed, well, according to the situation, all 12 ounces should be eaten. So there should be no ice cream left at all. Okay, so we can use these two ordered pairs. So this is the ordered pair 0, 12, and this is another ordered pair 5, 0. Okay, we can use these two ordered pairs to calculate the slope, guys. Watch this. So that means that m, the slope, equals, let's let this one be x1, y1, that's x2, y2, so that should be 0 minus 12, and 5 minus 0 in the denominator, so that'll be negative 12 over 5, or, you know, negative 12 fifths. We can't simplify it any further. You can call it the mixed number equivalent if you really want to, but like who cares? Just leave it like that. Okay, so here is your slope, and here is your y-intercept. Y-intercept. So we can write the linear equation as follows. F of t equals negative 12 fifths t plus 12. Oops. Hold on, let me erase that real quick. Plus 12. Fun. Okay, so now we're being tasked with graphing the function. Okay, so let's go ahead and take black going on here. And notice that in the scenario, your time variable is always going to be positive, and the number of ounces of ice cream is, these things are always going to be positive. So it's kind of essential that we recognize this in order to draw our axes, which should be along the left vertical side and the bottom. That's going to make the most sense. There's no negative values for either inputs or outputs, so you shouldn't have any negative values possible in your graph. So here's your t-axis. Here's your f of t axis, okay? And we're going to have minutes, and it's 5 minutes total that need to be addressed. So I think every 2 tick marks will be fine. So here's 1 minute, 2, 3, 4, 5 minutes. And this is ounces of ice cream. Well, we got all the way up to 12, right? So 2, 4, 6, 8, 10, 12. Or we could have each 2 be like 3, 6, 9, 12, and then that'll be what, 15, just so it's spaced out really nicely. And then this is OZ of ice cream. So notice how I have labeled not only my tick marks, not every single tick mark, of course, but appropriate ones when necessary. And then I've labeled the axes as t and f of t, and I've also put the units of the inputs and outputs as well. I think all of this stuff is necessary here. Okay, so let's go ahead and use another color to plot ordered pairs. And in this case, we could do the plotting points method by plotting both the x or the y-intercept, which is here, and also this is the x-intercept. So we're using the intercept method technically in order to plot this. So I'll start at 0, 12, which is right here, and then we'll go 5, 0, which is right there. And it is a straight line from one to the other. Okay, so let me light up my little straight edge. Cute, and go for it. There we go. And you can plot some points in between just to make it like, you know, look more legit. But you don't have to technically like find the values of any of those. You know that they're supposed to lie on that line given that the relationship is linear, okay? So the domain and the range are any value for t for the domain that spans from 0 to 5, okay? So that means that the domain is t such that t can be anywhere between 0 and 5. And so since you want to grab every single possible value in between, it's more appropriate to do a compound inequality. Whereas, because you could never list all of the values between 0 and 5, including all the decimals in between, like that would be insane. So your range, therefore, is going to be similarly defined as your f of t, such that it ranges all the way from 0 to 12. Compound inequality is appropriate here as well. And there you go. Cool. So that is everything you need to know about functions at the moment. And so let's switch gears over to scatter plots, in which we're going to revisit this idea of explanatory and response variables. We've already defined these items, but we want to define them further and a little bit more specifically in regard to inputs and outputs. So your explanatory variable, here we go, is acts as the independent variable. Let's get my drawer in action. The independent variable. It could be anything. There we go. Of course, there are sometimes constraints given the context of the problem that determine appropriate values to choose for your explanatory variable. But it could be technically anything. I mean, unless there are domain restrictions, of course. Commonly referred to as X. And the response variable is dependent on what you chose on X. So it is the dependent variable. Commonly called y, or f of x if you're using function notation like we just talked about. But yeah, the most common way to refer to it is y. Okay, now generally the explanatory variable is the thing that comes first in a situation, and the explanatory variable is the thing that comes later or as a result of the explanatory variable. So we'll want to keep this in mind in tackling the next examples. So we want to, here are the instructions, consider each situation, so we'll read each prompt carefully. We'll identify the explanatory and response variables, and which one's the x-axis, which one's the y-axis. Well, let me let you in on a little secret. The explanatory variable is always associated with the x-axis, and the response variable is always associated with the y-axis. So that is a given. That's not something we'll need to think about. That's described the situation with an ordered pair, okay? So basically we're going to read these scenarios and then just identify some things. So here's number one. A person cooks a potato in an oven for an hour and then removes the potato and allows it to cool. Let T be the number of minutes since the potato was removed from the oven, and let F be the temperature in degrees Fahrenheit of the potato. The potato has a temperature of 85 degrees after 7 minutes. Okay, so this last sentence where it says the temperature happens after 7 minutes have passed, that should key you into the fact that the minutes have to pass first. So the minutes is the first thing that's happening to the potato, minutes in the oven. And then the temperature is going to be, um, the temperature of the potato is going to occur after it's been in the oven, right? So that's the thing that happens after. So it should be associated with the response variable, whereas the explanatory is the time allotted for the potato to be in the oven. Okay, so let's identify explanatory and response variables. So explanatory is time. Response is degrees Fahrenheit. Okay, which one's the x-axis? This one is the x-axis. Again, sorry, that's a little sloppy. The explanatory is always associated with the x-axis. The response is always associated with the y-axis. And then let's describe it as an ordered pair. Okay, well, the situation of 7 minutes elapsed, 85 degrees for the potato, there's an ordered pair. And I left the units out of it when we talk about this information as an ordered pair. Generally, we just want to be working with the numbers alone and leave the units out, okay? So there is all of the things that they asked me to do for this first example. Now, let's key into a different situation and identify all of those same elements, but for this new scenario, which reads as follows. Let P be the asking price in thousands of dollars of a home with B bedrooms. The asking price of a 3-bedroom home is $152,000. LOL, not anywhere around here anyway. Depending on where here is for you, I recognize that some people are not, haven't stayed into town since everything went remote. Anyway, the thing that we want to do here is ask ourselves, well, what is being considered first in the scenario, and then what is the resulting value of that first thing being considered? Well, the way I see it is that you talk about how many bedrooms there are first, okay? So I see the explanatory variable as being the number of bedrooms. So I'll say number of bedrooms. And then depending on the number of bedrooms, we have the asking price, P. Number of bedrooms, we'll call it B. And then the response is the asking price. Asking price, P. Always, this is the x-axis, right? Like this part of it, we do not even need to think about. This is the y-axis. And then the ordered pair associated with this last sentence would be a 3-bedroom house is $152,000. Oh, asking price P in thousands of dollars, let's say. I didn't mention that before, but it's definitely worth noting. So you can work with smaller numbers in the midst of your ordered pair, which would look like that. Okay, let's move on to the last example in this set, and then we'll move on to something else within the scatter plot section. A person goes for a run. Let S be the runner's speed in miles per hour, and let P be the runner's pulse rate in beats per minute. When the runner's speed is 10 miles per hour, his pulse rate is 160 beats per minute. Okay, I see the situation is going this way in a timeline sense. First the runner runs, then they take their pulse rate, right? So you can't take your pulse rate unless you have already run some distance, because it wouldn't make any difference in regard to the scenario, because you want to be taking your pulse in regard to implementing some exercise, i.e. the run. So I see the explanatory variable as the speed of the runner. Runner's speed. Which is S in miles per hour. I'll call it an MPH. And the response variable is the pulse rate. Beats per minute. and sorry, P is the variable in beats per minute. And then, of course, this is x-axis. This is y-axis. Duh, we knew this. And then the ordered pair. Let's say we were going 10 miles per hour, and the pulse rate was 160 beats per minute. X and Y respectively in those positions for the ordered pair. Cool. We could certainly talk about that and anything else when we get back into class about this. Okay, now it's time to legit talk about scatter plots. So what is the idea for a scatter plot? It's basically a way of representing ordered pairs. So plotting ordered pairs in a coordinate system. So this is a way to plot ordered pairs in a coordinate plane. And really the purpose of it is to look for a pattern. We'll talk about such patterns that could arise in regard to making scatter plots. So here's an example of a scatter plot. Exercise versus obesity. Okay, so on the horizontal axis representing the explanatory variable, we have the percentage who exercise, and then the response variable, therefore, is the percentage who are obese. Okay, an example, exercise versus obesity, we want to let X be the explanatory variable and Y be the response variable, and to construct a scatter plot of the ordered pairs listed in the table. Okay, so yeah, sorry, this graphic actually has nothing to do with this this next thing right here. This example is just is separate. We actually just want to practice making our own scatter plot. So one thing that we'll need to do is consider the domain and the range and determine where our axes should go in the grid that was provided. So I already pre-counted the bottom edge there and found that there were 15 boxes, and so it's a 15 by 15 square, right? So notice that the y value goes all the way out to 15, you know, and all of the y values are positive, and the x values range in value by -16 wide, actually. So what I think is best to do is kind of offset this a little bit, with the vertical axis being, oh, I don't know, maybe about here. Oh, and let me switch it to black. I like to draw my axes in black. So something like this, I think, would be appropriate. And every box is going to represent 2. Okay, so we should offset the make more positive x's than negative x's, and then pretty much no, let's make no, or, you know, we could just make 1 or 2, whatever, it doesn't really matter. Values, since there's no negative y's, right, it doesn't really matter. So here's the x-axis, here's the y-axis. Now again, why am I putting my x and y axes in these positions? Because I'm looking at the ordered pairs that we're going to plot, and I want to make sure that we get all of them, okay? So here we go. Let me change the color to, what's something that I haven't used? Let's use this orange, or no, let's use this like really bright orange color. All right, so here's -5, 2. Now remember, every box's length is going to represent 2 values here. So let's go to -5, which would be here. So that's -2, -4, and then halfway between -4 and -6, -5, and then we'll go up 2. So that should be right there. Here's -5, 2, okay? -4, which will be right here, and go up to 3, that's here, right? And then -1, which will be right here, will go up to 5, which is right in the center there. 4, 9, so 2, 4, and then up 9, so that's 2, 4, 6, 8, 9. And then 11, 15. Now we're going to go out pretty far for this one, so let's go out to 11 in the x sense, so that's 2, 4, 6, 8, 10, and then 11. and then up 15 from there. So that's 2, 4, 6, 8, 10, 12, 14, 15, right there. Okay, so maybe I have a little bit more extra space than I needed to, but better to have some extra space than to make it too tight, okay? So as you can see, this is looking like it's lying pretty much on a line or very close to being on a line. And if it were lying on a line, wouldn't that line be having a positive slope? So having a positive slope for the what we would call the line of best fit, not that that's something we really get deep into in this course, it would be having a positive slope, and therefore you would say that this data has a positive association. We'll get to that in just very shortly. Okay, but here we go. I went ahead and constructed a scatter plot for the ordered pairs. That is done by virtue of what you see in the grid. Okay, cool. Now let's do this again, but for this particular context problem. We're talking about the total fuel cost for global online industry as shown in the table below for various years. Cool. So let's see, be the total online fuel cost in billions of dollars as you see it in this table right here. And that's going to be your response variable, and the explanatory variable is going to be t years since 2005. Okay, so that means that t, I can make another column here, which is going to be the explanatory variable. Years since 2005, that means that this first one's going to be a 2, then 3, 4, 5, and 6. We'll keep that in mind, okay? So we're not going to actually use these years in order to plot, okay? So yes, let's go ahead and identify the explanatory variables are t years since 2005. The response is the fuel cost in billions of dollars. And they're calling it C. Fuel cost in billions of dollars. Okay, scatter plot away. Now, years and cost, that's all positive. So here it's going to be easy for us to draw the axes. They should be all the way to the left for the vertical axis and the bottom on the horizontal axis. Okay. So it's T here, C there, cost of fuel in billions of dollars, in billions of dollars. And then T, this is years since 2005. And what number did we go up to for that? 2 to 6. Okay, so here's 2, 3, 4, 5, 6. No issues plotting all those there. And then let's see, we go from 133 up to 174. So maybe we'll do every 5 will be 1, 2, 3, 4. 1, 2, 3, 4, 5. Maybe this will be 100. That'll be 200. Okay, I think that'll be good. Sure. So here is 150. Here's 50. You just draw some more tick marks in there just to make it a little easier. Okay, great. Now I think we're ready to draw the scatter plot, and I'm going to change the color of, just get my dots going in there. Let's do this electric blue. That's cute. Okay, so at 2, we are at 133 billion. So where should that be? Well, here's 150, so 133 will be like, oh, maybe about right there. We're just doing our best to estimate this. And for 3, it's 187. which is closer to 200. Maybe it's like a little bit above here for 3, something like that. That's about 187. And then we go back down to 1, 2, 3 for the 4th year. 1, 2, 3. So here's a 125-ish, so somewhere around there. And for the 5th year, we're at 138. 138. 138, so that should be up a little bit more, like here-ish. And then for number 6, 174, so back up again. Sure. Something like that. Kind of all over the place. It doesn't seem like there's a very clear association here. Something that we'll get deeper into a little bit later. Okay, but yeah, there you have it. So there's your scatter plot for fuel and cost of billions for those 5 years. Okay, moving on. Yes, let's now talk about positive and negative association. Something that I've been alluding to here, but let's get into it very much more specifically. Okay, so it says that assumed 2 numerical values are the explanatory and response variables of a study. If the response variable tends to increase as the explanatory variable increases, we say that the variables are positively associated. Positively associated. And that there is a positive association. I know. A little bit circular there. Just want to make sure we have all the correct terminology out there. Conversely, if the response variable tends to decrease as the explanatory variable decreases, we say that the variables are negatively associated. And that there is a, you guessed it, negative association. In order to marry this to ideas that we've already formed, positive association graphically looks like a more or less a line with a positive slope, so increasing as you move from left to right on your coordinate plane. Negative associations look like lines with negative slopes. So if you can draw what you deem to be something close to a line of best fit, and it seems to have a positive slope for the scatter plot, then you'll say it's positively associated. So for instance, I would see this as probably a good line of best fit for this data, because the data is like, jumping above and below this line, so to speak. I would say that this is representing a positive association. I would see this as having a negative association. And this scatter plot, I mean, depending on what part of it you look at, it could be having a negative association or a positive one. So since it has both at the same time, we would say it has neither positive nor negative association there. In fact, the association looks parabolic, which is something completely different that you'll be getting into in your next level class, Math 54. That's it for today. Thank you so much for your attention. Let's talk about this stuff in class next time we meet.